In this video, we're going to focus on finding the tangential and normal components of acceleration. So we know that acceleration, which is the second derivative of the path, is a linear combination of our unit tangent vector and our principal normal vector. The reason why we're talking about acceleration and kind of skipping over velocity is that velocity is just a scalar multiple of our tangent vector, or of our unit tangent vector, and which means that the magnitude, or the scalar up front, is the magnitude of velocity, which is just speed. So there's not much interesting going on in velocity case. There is more interesting going on in the acceleration case. So we can write acceleration as a linear combination of these two things using a couple of formulas. We can find the tangential component, so the scalar that goes up front here, by taking the derivative of speed. So how would we do that? Well, remember that speed was the magnitude of the derivative. And we already found that as square root of 8t squared plus 9. So if we want to find the derivative of that, we're going to need to use the chain rule of 1 over 2 times 8t squared plus 9 times derivative of the inside, which is 16t. Some things cancel, and we end up with 8t over the square root of 8t squared plus 9. So what that tells us is that if we're writing acceleration as a linear combination of our tangent and normal vectors, this is going to be, the part in front of t will be 8t over square root of 18 squared plus 9. And we call that at, or the tangential component of acceleration. Now there's two formulas we have for the normal component, what goes in front of n. And since this first one involves the curvature, we already found the curvature, so in this case it might be easier to do this one. But if you recall, finding the curvature was awful. We had a slightly easier way to do it, but it still wasn't particularly nice. So usually we don't have the curvature, and this one's too much pain. But since we have the curvature, let's go ahead and use it. So the normal component is going to be equal to the curvature times the speed squared, which in our case, the curvature was 6 square root of 2 over square root of 8t squared plus 9 times, and then our speed squared is just going to be 8t squared plus 9 with no square root. I lied about that being the curvature. This is actually to the third power, or 8t squared plus 9 to the 3 halves. And when we simplify that out, that's going to be 6 square root of 2 over just the square root of 8t squared plus 9. And that should be our normal component of acceleration. So I can write here 6 square root of t over square root of 8t squared plus 9. Now, let's say we didn't have the curvature and we didn't feel like doing the work to find the curvature. We have another formula that relates the norm of acceleration squared and the tangential component to the normal component. So what we can do is we can start by finding what is the norm of acceleration squared. With that, we should start by finding acceleration. Acceleration is the second derivative of our path. The first derivative of our path, if you remember, was 2t, 3, negative 2t. So acceleration is just going to be 2, 0, negative 2. And the magnitude of acceleration squared is just going to be 4 plus 4. Normally it would be square root of 4 plus 4 if we didn't have the square, but since we're squaring it anyways, let's just drop the square root. So it was easy enough to find acceleration squared. We already found the tangential component, so it's easy enough to square that. The tangential component squared is going to be 8t squared. Sorry, that's 64t squared. Over square root of 8t squared. No square root because we're squaring it, so that's nice. 64t squared over just 8t squared plus 9. So we're saying that the normal component of acceleration should just be the square root of 8 minus 64t squared over 8t squared plus 9. Is that what we got earlier? It kind of looks like no, but we should give it a fair shot to see if that's actually the case or not. So we can think of multiplying this first one by 8t squared plus 9 over 8t squared plus 9. That'll give us 64t squared plus 72 minus 64t squared over 8t squared plus 9. We notice those 64t squareds cancel. This will be the square root of 72 over the square root of 8t squared plus 9, which is in fact 6 square root of 2 over square root of 8t squared plus 9, which is what we got earlier. And this way, we didn't even need to find the curvature. I'm not going to say it was easy, but I would say it probably is easier than having to find the curvature, because we needed to find at least the acceleration anyways to find the curvature. So this one didn't involve taking a cross product or anything. We just had to find some magnitudes. So there you go. That's how you can find the tangential and normal components of acceleration in a couple different ways. So there you go.